This is Dr. Anthony Revis, and this is SVSU General Chemistry 111, Chapter 8, Lecture 1, Advanced Theories Covalent Bonding. That's Lecture 1 of Chapter 8. In this chapter, we will cover valence bond theory, hybrid atomic orbitals, and multiple bonds. These topics will be covered, however, they might not be covered in this particular order. What is valence bond theory? Valence bond theory is a theory that describes a covalent bond as the overlap of half-filled atomic orbitals, each containing a single electron, that yield a pair of electrons shared between the two bonded atoms. In other words, valence bond theory describes how we make covalent bonds. Covalent bonds are made by the overlap of a single electron from one atom with a single electron of another atom. They come together, the orbitals overlap, they share the electrons, one spin up, one spin down, and that makes a chemical bond. In the case of where there's one electron shared with one electron, that overlap results in a single bond. We will be talking about that in more detail. So, we make chemical bonds from valence electrons where they overlap to form a covalent bond. We say that the orbitals on two different atoms overlap when a portion of one orbital and a portion of the second orbital occupy the same region of space. In other words, they find a way to meet in the middle such that the overlap creates this new chemical bond. According to valence bond theory, a covalent bond results when two conditions are met. So you need two conditions to form a covalent bond. One, an orbital on one atom overlaps with an orbital on a second atom. The second condition is the single electrons in each orbital combine to form an electron pair. And an electron pair requires that there be opposite spins. Recall when we talk about the Pauli exclusion principle, meaning that when electrons enter the same orbital, one must be spin up and one must be spin down, one's plus and one's minus. And the magnitude is plus 1/2 minus 1/2 to create stability. Valence bond theory also teaches that the mutual attraction between the negatively charged electron pair and the two atoms' positively charged nucleus serve to physically link the atoms through a force which is defined as a covalent bond. So when they combine, the force that occurs or the force that allows them to bond is called a covalent bond. So essentially what you have is you have an atom, we'll call it atom A. It has its electrons, and in the nucleus you have protons and neutrons. The protons are the positively charged. That proton matches the atomic number on the periodic table. And so we have atom A, then we have the same thing for atom B, or likewise for atom B. Electrons in the nucleus, then we have the protons and the neutrons, again in the nucleus, for protons and neutrons, positive center, they come together, there's a force, that force is called a covalent bond. So covalent bonds are formed when atom A with its one electron and atom B, two independent atoms come together and form a bond between them. That bond will be composed of at least two electrons to make a single bond. Now, the strength of a covalent bond depends on the extent of overlap of the orbitals. So, the greater overlap, the stronger the bond. Orbitals that overlap extensively form those strong bonds. And when they don't overlap as well, it is a weaker bond. So, essentially, we have the two orbitals of the different atoms. They come together, they hybridize, they mix, they find an overlap where the energy is lowest, where they can find a relationship that stabilizes both centers. And when that happens, it's going to be called a covalent bond. The amount of energy in the system will depend on how much the orbitals overlap. We show you here an example of hydrogen. Let's take a look at the diagram first on the left of this slide. In this diagram, what we're showing you here is there is energy on the y-axis and there is internuclear distance on the x-axis, the horizontal axis. And what we're showing you here is that these two hydrogen atoms, shown near the top of this diagram to the right, when they're far apart, we have naturally two independent atoms. But at some point, as these atoms move closer together, moving to the left, they move closer together, they eventually find this low energy position shown near the bottom of the slide where we form H2, which is diatomic hydrogen. And when they form that, it forms at a bond length of 74 picometers. That distance is where the two atoms coming together achieve the lowest overall energy for the system. So the bond length represents the lowest energy distances of the two atoms. So let's repeat this. Ready? Orbitals begin to overlap as atoms move closer. Electrons feel the attraction of the nucleus in the other atom. Electrons also begin to repel each other. They're both negative, as do the nuclei. Attractions are slightly stronger than the repulsions, however, when atoms are still widely separated. And the energy of the system is decreased at that point. So when they're further apart, there's less energy. As the atoms move closer together, the overlap increases towards optimum distance where the bond is stable, which is the point at which the attractive and repulsive forces result in lower energy. That's how we form bonds, we form new compounds from the interaction of valence electrons. In the case of hydrogen, the interaction of two hydrogen atoms changes with distance. That same thing happens for all atoms coming together. The two atoms change, the interaction changes with distance. The energy of the system changes as the atoms interact. So you have this moving scale, if you will, of energy. And it moves until that energy is optimum. The lowest, most stable energy occurs at a certain bond length. Again, in the case of hydrogen, it's 74 picometer. Okay? That is the bond length of an HH molecule. So that's how we form bonds. And in this particular case, this is how hydrogen formed a single bond. This table shows you bond lengths for other atoms and other covalent bonds. The bond length again is established by the overlap of the orbitals. And here we don't expect you to memorize this table, but you just take a look at it and you see depending on the atoms we get different bond lengths. And there's a different amount of energy associated with each of those bonds. Those are important principles that you want to take away from this, is that when atoms overlap, they establish an ideal bond length, and here we show you the ideal bond length for a variety of compounds. Note that the shorter the bond, the larger the energy. That's an important principle. Again, the shorter the bond, notice the bond length, the higher the energy. Okay, so be aware of that. So a triple bond, for example, of carbon, has a shorter bond length, but it has a higher energy. So the two are inversely proportional within a series of like atoms. So be aware of that. So take a look at this table and just become familiar with the trends that you see. This is all explained by valence bond theory. Now, in addition to the distance between two orbitals, the orientation of orbitals also affects their overlap. In other words, how the two orbitals face each other or align with each other is an important factor. Now, in the case of an s orbital, which is a sphere, there is no orientation there. It's a sphere, so the overlap is the same. But in case of p orbitals and other orbitals, we can have head-to-head, or we can have side interactions, or back-to-back, depending on your view of the orbital. We can have those different alignments, and that alignment affects the overlap, which means it affects the energy in the bond. Greater energy is possible when orbitals are aligned such that they overlap on a direct line between the two nuclei. We show you in this particular example where we have alignment A and B, the head-to-head, if you will, straight on in a straight line, accommodates more overlap than when they're tilted on their side. So you'll want to be aware of that. End-to-end overlap of two p orbitals are called sigma bonds. Sigma bonds are single bonds. That's important. So when there's end-to-end overlap, it forms a single bond, which is called a sigma bond. There's also an alignment where the two orbitals align side to side. That side-to-side alignment is called a pi bond. So we have sigma bonds and we have pi bonds. Those are the principal bonds that we will be discussing in the remainder of this chapter. Sigma bonds and pi bonds. So the orientation and alignment is critical to the type of bond that's formed. So valence bond theory involves the overlap of electrons. More specifically, it involves the overlap of valence electrons. So let's review what valence electrons are and discuss the principles related to valence electrons in more detail. Valence electrons are the outer shell electrons of an atom. The valence electrons are the electrons that participate in bonding. These are the electrons that overlap to form new bonds. We show you here the electron configuration of the groups that we are paying most attention to in freshman chemistry. Group 1, 2, 13, 14, 15, 16, and 17. Note also the A designation of these periodic table groups. We have the electron configuration. From that electron configuration, we can determine the valence electrons. And the valence electrons follow 1, 2, 3, 4, 5, 6, and 7 in terms of its valence electron count. You should also recall that to determine the valence electrons, we simply count the number of electrons in its highest N period. And we also note that group 18 is a closed octet, and we do not consider its valence electrons in discussions of bonding. Noble gases do not bond with other atoms. When atoms combine, there's also a lower energy geometry that they will acquire. That lower energy geometry is described in what's called VSEPR structures. So what are VSEPR structures? The arrangement of electron pairs around a center atom in a molecule or ion is known as VSEPR theory, which is known as valence shell electron-pair repulsion theory. Electron pairs repel each other in real molecules. In other words, when these atoms come together to find that lower energy position, there is some positioning based upon its electrons, based upon its electron density and the distribution of the electrons and the count of those electrons. They distribute themselves in positions around the central atom that are as far away from one another as possible. When it does this, it forms a particular angle. The angle formed by two electron pairs in the central atom is what's called the electron-pair angle. So, you're going to hear more about repulsion of electrons, which in a practical sense is repulsion of the atoms. You're also going to hear more about the bond angle. And we discussed this based upon our understanding of valence electron theory. And the geometry involved in valence bond theory is called VSEPR theory or VSEPR structures. And we're going to take a look at those structures based upon their geometry, which will involve the electron pair angle as well. So basically, we'll be looking at the geometry, and that geometry is the result of valence bond theory. You will need to memorize a lot of this material. However, it is pretty systematic, and once you see the system and it starts to make sense, the memorization becomes easier. It is fairly systematic, and is a systematic approach to examining the geometry of these compounds that result from valence bond theory. So let's talk about the VSEPR models, and we're going to talk about them throughout a fair portion of the rest of this lecture. Okay? So VSEPR models, VSEPR shell electron pair repulsion. That's what VSEPR means. So the VSEPR model helps you to predict the geometry of the molecule from the electrostatic repulsions between the electrons, bonding and non-bonding, in association with the atom. We look at the electrostatic repulsion between the electron pairs. Now, when we look at the electron pairs, we will be looking at atoms as well. So, we will be talking about atoms, and we will be talking about lone pairs. So, there will be repulsion between the atoms, and there will be repulsion involving lone pairs. To think about this theory, you want to start to think about the space occupied by the atoms surrounding the central atom. The key is to focus on the central atom. That is an important principle moving forward. We are examining the structure based upon the atom distribution around a central atom. What geometry results from that distribution? What is the angle related to that distribution of atoms and lone pair electrons? When we talk about the VSEPR model, it will be organized repeatedly as shown here on this slide with an occasional modification. It will be organized according to the class, the number of atoms bonded to the central atom, the number of lone pair, the arrangement of the electron pair, and the molecular geometry. So this is how we will describe our VSEPR models. The class for this first VSEPR model is called an AB2. The A will represent the central atom. The B2 represents the number of atoms or electron pairs associated with the central atom. And what happens when the atoms or electron pairs are attached to the center atom, they will repel each other until they can find the lowest energy position. And that position is as far away from each other as they can get. So in the case of having a central atom with two things flanking it, that's 180 degrees, which means you get the arrangement of electron pairs shown here, and you get the molecular geometry shown here. So we'll talk about the electron pairs, and we'll talk about the molecular geometry. Okay? So you get it? That's what it will do over and over again. You will have an attachment of atoms and lone pairs to the central atom, and the groups will repel each other to find the lowest energy position, and that is what your bonded geometry will look like. The next one will be an AB3, central atom A with three groups around it. In the case of an AB3, it's three atoms, no lone pairs. It will form a trigonal planar geometry because that is the ideal distance for three atoms located around the center. It's a matter of geometry. Now keep in mind that geometry is 3D, and you will see that effect happening very soon in some of the structures. So the arrangement of electrons will be trigonal planar, and the molecular geometry will be trigonal planar as well. What's the difference between the arrangement of electron pairs versus the molecular geometry? The arrangement of electron pairs show where the electrons are, where the electron density resides. That's causing the repulsion. The molecular geometry is that same electron pair orientation with the exact atoms affixed to those positions. So we have AB2 for linear geometry. We have AB3 for trigonal planar geometry, meaning it's flat against the board or flat against the desk. Now we have AB4, which takes on more of a 3D orientation. Number of atoms bonding to 4 and no lone pair. The ideal position for the distribution of the electron pairs is 109.5 degrees. Again, it's a matter of geometry. That forms what's called a tetrahedral. You will learn as we move forward that this tetrahedral orientation tends to be a popular arrangement of electron pairs for many other molecules. That tetrahedral is retained when we add atoms to where the electrons are. And in this case, we have 4 atoms located where the electron density is. And they're arranged for the lowest position of energy according to the valence electron theory. These atoms approach the central atom. They found an ideal position at 109.5 degrees, which created its ideal bond length for the lowest energy geometry. That geometry is represented by what we call the VSEPR model. I'd like to remind you that when we do VSEPR models, we think of the organization around the central atom. Let's take a look at some examples we show you here. We have beryllium chloride, linear. It has an AB2 geometry. We show you that, 180 degrees. We show you here an AB3 example. That would involve something from group 13, like an aluminum chloride or boron trihydride, which would have a 120 degree angle. The tetrahedral would involve many different atoms, many different molecules. For example, methane is the classic example that's used. And that geometry is such that the angles are 109.5 degrees for its lowest energy geometry. As I already pointed out to you, the tetrahedral geometry tends to be a popular geometry for the arrangement of many structures the arrangement of the electrons around many central atoms. Here we show you what that might look like for different compounds. Starting with the classical methane, we have our tetrahedral geometry, which is an AB4 geometry. In this case, we have these 5 atoms that have come together with 4 bond pairs, so 4 sigma bonds, 4 single bonds, and there are no lone pairs on the central atom. Again, we like to remind you we're doing the geometry of the central atom. So, for silicon tetrachloride, we have, again, a tetrahedral geometry. This is a tetrahedral electron-pair geometry. And there are 4 atoms attached to the electron-pair positions, the 4 electron-pair positions. Now, we can take that same geometry and use it in a 4-atom molecule in the case of ammonia or ammonium trichloride, for example. So here, we take that geometry and we fill it with 3 bonded pairs and 1 lone pair. We fill the 4 electron pair positions with 3 atoms and 1 lone pair. The VSEPR structure resulting from that core tetrahedral geometry is called a trigonal pyramidal. In that case, we only have 3 atoms, and the other electron pair position in that classical or core tetrahedral geometry is a lone pair. We will use a similar geometry for the electron pairs to form a bent water molecule. And in the case of a bent water molecule, bent or angular, in the case of that molecule, water, it would have 3 atoms, in which case the 2 bond pairs take up 2 electron pair positions and 2 lone pairs take up the other 2 electron pair positions. So we would have water, or we could have, for example, sulfur dihydride. So let's repeat this. There's a core geometry that takes advantage of the approximate 109.5 degree angle for a central atom having 4 electron pair spaces. When those locations are filled with atoms, that is a tetrahedral. When 3 of those spaces are filled with atoms and 1 space is filled with a lone pair, that's called trigonal pyramidal. And when 2 spaces are occupied by atoms and the other 2 spaces are occupied by lone pair, that's called a bent or angular geometry. This is the VSEPR structure for what might be described as a core electron pair geometry having the tetrahedral form. Depending on the atoms at that electron pair region, or whether it's electrons at that electron pair region, the bond angles will shift slightly. In the case of methane, you would have the classical 109.5 tetrahedral angle. In the case of ammonia, that bond angle would shift to be more tighter on the hydrogens because of the electron density of the lone pair occupying that pyramid position. The bond angle would then be 107.3 degrees. And then in the case of water, that bond angle is pushed in even tighter because of the 2 lone pair. So you should be able to predict whether or not the angle is going to expand or contract depending on the lone pairs or depending on the groups attached. Let's continue on to look at some more interesting geometries. We've gone through AB2 for linear, AB3, trigonal planar, AB4, tetrahedral, and now we have AB5, trigonal bipyramidal. So for the trigonal bipyramidal, you essentially have two pyramids stacked on top of each other. In this case, we have 5 geometrical locations to fill around the central atom. When that's the case, we get a bond angle that's shown here of 120 degrees. Essentially, in the middle of this is a trigonal geometry that has a pyramid on the top and the bottom. And so we have these arrangement of the electron pairs in this fashion, and we can fill those with atoms if that's what this particular compound can accommodate for the geometry shown here. So we have the electron pairs and we have the molecular geometry. The molecular geometry takes atoms and places them at the locations of the electron pairs. And in this case, there are 5 locations. We can continue to build further with these structures. In the case of now an AB6, we have an octahedral shape geometry in which there are 6 electron pair regions that we can fill with atoms, or we can partially fill with atoms, and the other locations would have lone pairs. We show you some examples here of a trigonal bipyramidal. Would be an AB5, would be 120 degrees between the 3 horizontal spaces, and the space between the apex of the pyramid down to the base would be 90 degrees. If we have an AB6, you see the geometry shown here. We have a series of 90-degree angles that form this octahedral shape. And this octahedral shape is the lowest energy geometry based upon the Valence Bond Theory. Now, in these next slides, you're going to hear a discussion that sounds like what you've already heard. And, frankly, it is. However, we're going to show you now how to be more specific in your nomenclature of the class to describe whether you have atoms surrounding the central atom, that is, bonded groups around the central atom, or whether you have electrons, or actually a combination of lone pairs and atoms surrounding the central atom. So, the system will be the same, but we will be more specific to define whether or not they're atoms from the periodic table or lone pair. And with that comes the specific nomenclature for that geometry. They're all VSEPR structures, but with more specificity. Let's take a look at it. We have our classical AB3 classification. In this case, we could have 3 atoms. If we have 3 atoms and no lone pair, that is AB3 for a trigonal planar arrangement of the electron pairs. And that is a trigonal planar molecular geometry. We talk about molecular geometry because these are true covalent bonds. And in this case, we're talking about covalent single bonds. Now, if we take that AB3 and substitute in a lone pair, we would describe that as E. So we would have an AB2E, which would tell us that we have 2 bonded atoms and 1 lone pair. So if I see an AB2E, I I know I have 2 atoms, 1 lone pair. If I see an AB3, then I know I have 3 atoms. Okay? So, for the AB2E, with 1 lone pair, E meaning 1 lone pair, we have a trigonal planar arrangement of electron pairs. However, the molecular geometry is bent. It is important that you differentiate between the arrangement of the electron pairs and the molecular geometry. Take care to listen to exactly what you're being asked. If it talks about the arrangement of the electron pairs, it is trigonal planar. If it talks about the molecular geometry, it is bent or angular. And that is important. So, one of the things you've now learned then is that you can have a molecular geometry that is described as bent while its arrangement of electron pair is trigonal planar. Let's take a look at a 4-electron group, an AB4. An AB4 would have 4 atoms bonded to the central atom. I'd like to remind you that when we talk about the VSEPR model, we're talking about the geometry about the central atom. So an AB4 has 4 atoms about the central atom and no lone pair. In this case, the arrangement of the electron pairs is a tetrahedral. And since there are 4 atoms at those electron pair positions, its molecular geometry is tetrahedral as well. On the other hand, if you take an AB4 classified structure and substitute one of the B groups with an E for a lone pair, you would have 3 atoms, 1 lone pair, arrangement of electron pairs, still tetrahedral. However, the molecular geometry is trigonal pyramidal. Be aware of that. The arrangement of electron pairs does not always tell you what the molecular geometry is. What tells you what the molecular geometry is whether or not the central atom is surrounded by other atoms from the periodic table or from lone pair electrons. So you will have to learn to make that differentiation. So an AB3E and an AB4 have the same arrangement of electron pairs. However, the E has a trigonal pyramidal geometry and the AB4 has a classical core tetrahedral molecular geometry. Let's continue with another 4-electron group. We have the AB4, which has no lone pair, therefore arrangement of the electron pairs is tetrahedral, and the molecular geometry is tetrahedral. The AB4 has 1 lone pair substituted at one of the positions. It becomes a trigonal pyramidal molecular geometry. If we substitute 2 of the atoms or 2 of the position with electrons and 2 with atoms from the periodic table, we have 2 atom arrangement with 2 lone pair. It is still an electron pair tetrahedral geometry. However, its molecular geometry in this case is bent or angular. So, you note that you can have again a tetrahedral core with at least 3 different molecular geometries. You will want to be aware of that when you're making these assignments. That just because the arrangement of the electron pairs has one geometrical shape or one geometrical notation, its molecular geometry can be and oftentimes is different depending on the arrangement of electrons or the electron count of lone pairs. Let's take a look at an AB5. An AB5 with 5 atoms, no lone pairs, has a trigonal bipyramidal for its electron pair arrangement, which is also the exact same molecular geometry of compounds with this AB5 classification. If we substitute in one position with a lone pair, that creates an AB4E, E for the electron pair. The arrangement of the electron pairs is still the same. It's trigonal bipyramidal. However, its molecular geometry is distorted tetrahedron. Distorted tetrahedron is a tetrahedron type shape that has been distorted by the repulsion of the other groups by the lone pair. So the lone pair has essentially pushed the other atoms back to make more space for it. So the bond angles have moved from an expected 90 degrees to a lower value for most of the atoms and a larger value for the crowded lone pair. So this is what valence electron theory helps us to understand and visualize. It helps to visualize the electron density around an atom or one of the geometric positions in the VSEPR model structures from the valence bond theory. We get a good idea about the influence of electrons, electron density, and atom spacing on the molecular geometry. So what happens if I substitute two of the bonded atoms for two pairs of electrons? In that case, we maintain our same arrangement of electron pairs as trigonal bipyramidal. However, the electron repulsion by the two lone pairs tends to distort the molecular geometry even further into what's called a T-shaped molecular geometry. And that's because of the repulsion of the two lone pairs. You will want to take a look at these and think through this. The key is to note that when we have lone pairs, that electron density tends to push back against the atoms on the structure. In the AB3E2 structure, the geometry starts to get distorted. But it's interesting that if you substitute in one more electron pair, the energy finds a way to reset itself, to redistribute the electrons, or at least the electron pairs, and the two remaining atoms to get what's called a linear structure. That linear structure, however, is different from an AB2. In this linear structure, we have three electron pairs occupying those other geometrical locations. And because of their repulsion and their need to lower their energy, it pushes the two bonded atoms to be 180 degrees apart. That gives it its lowest energy geometrical shape. And its molecular geometry is then linear. Let's look at the octahedral. We have the AB6 for the octahedral. Its arrangement of electron pairs is octahedral, and with 6 atoms surrounding the central atom, its molecular geometry is octahedral. If we substitute in one electron pair for the atom, it becomes a square pyramidal. The lowest energy position is one in which the lone pair is located at the apex of the geometrical shape. In this case, it's on the bottom of the geometrical shape, with the other groups forming the square pyramid. If we substitute in 2 electron pairs for an AB6 geometry, the lowest energy geometry for this is for the 2 lone pairs to be completely opposite, one at the top and one at the bottom of the geometrical shape for the octagon or for the octahedral. When this is the case, we form what's called a square planar geometry. In other words, we went from a pyramid geometry to a square planar geometry in which the groups are spaced 90 degrees from each other. This is the lowest geometry for this type of classification, for an AB4E2 classification. So, valence bond theory allows us to understand why molecules have a certain geometry. That geometry is established because that is the lowest energy geometry. That occurred when atoms were attracted to the central atom and there was bond overlap to form a single bond, a sigma bond. In some cases, there are electron pairs, and those electron pairs will cause the geometry to be distorted in a particular direction, depending on where it's located. In that case, the molecular geometry will rearrange itself or will find a way to move toward the lowest energy position for that molecule, and that will be its most stable geometry. So let's review some molecular structure examples. So we want to use the VSEPR model to determine the molecular geometry of the compounds shown here. And these compounds will form through valence electron theory, overlap of electrons, one spin up, one spin down to form sigma bonds, and we have this geometry that's based upon repulsion theories of electrons. And we know that these atoms seek to find the lowest energy geometry. So we take a look at ASH3. We have 3 electron pairs plus 1 lone pair. We know that once we draw out the Lewis structure. By using the Lewis structure, we can determine what the VSEPR classification is. It's an AB3E. Why AB3E? There are 3 groups surrounding the central atom. A, the central atom. B, the bonded groups. E, the electron pair or electron pairs. In this case, it's 1 electron pair, 1 lone pair. Therefore, it's trigonal pyramidal. If we take a look at OF2, we see that we have 4 electron pair around it. Of those electron pairs, we have 2 lone pairs, 2 E groups. That is an E2 group, and we have a B2 group, 2 bonded groups. When we look at that geometry, we've either memorized it or we can see the repulsion of these lone pairs, pushing it into a bent molecular geometry. If we take AlCl4 minus, we draw out the Lewis structure, and that's why it's so important to draw out the Lewis structure. One of the mistakes that's often made is seeing the minus charge. When we see that, we tend to think that's one more electron pair taking up a position. But that is not the case. If we look at the charge around the central atom aluminum, we note that the original count around aluminum should be 3. So we take 3 minus the count that's around it, which is 4. 3 minus 4 gives a minus 1 for an overall minus 1 charge on this. I did that using the quick count method. So by whatever method you use, we find that there are no extra electrons filling an electron pair space. So we only have 4 electron pair spaces around the aluminum. That's an AB4 because they're all filled by atoms for a tetrahedral geometry. And then we have I3. We take a look at I3 and we draw out the Lewis structure. Similar argument about determining the charge on the compound. It's a -1 charge. We look at the Lewis structure and we see it is an AB2E3 classification. With that classification, the electrons find the lowest energy position. The electrons plus the bonded elements find the lowest energy position in a linear molecular geometry. So, what we learned then is we can look at these atoms, and based on whether it has atoms at the geometrical positions or electrons at the geometrical positions, we can determine the VSEPR molecular geometry, and this is all based upon our understanding of valence bond theory. We show you a summary chart here just so you have it as a point of reference. So please note that in lectures where we talk about valence bond theory, occasionally you'll hear me and others like me say valence electron theory. So the term valence bond theory and, for some of us, valence electron theory are synonymous. So be aware of that. Valence bond theory is what we're talking about in this chapter. So let's summarize. Valence bond theory teaches that mutual attraction between negative charge pairs and the 2 atoms that are positively charged in the nucleus will attract each other to form bonds. Essentially, an electron from A and an electron from B will combine in the middle, spin up, spin down to form a covalent bond. The extent of that overlap is what determines the bond distance and the bond strength. When those bonds come together, they seek the lowest energy position, and that low energy position determines what the bond distances will be. In valence bond theory, the orientation of the orbital overlap leads to either sigma bonds with a head-to-head or pi bond with side-to-side overlap. The valence bond theory works because it involves valence electrons, which are the outer shell electrons in atoms. The outer shell electrons are the electrons that undergo bonding to give us new compounds from the overlap of electrons between atoms. We can show the resulting geometry based upon the VSEPR structure theory. The VSEPR structure theory helps us to visualize the distribution of atoms and electron pairs around a central atom. There are different combinations of atoms and electron pairs that come together around a central atom to give different arrangements of the electron pairs, and that also result in different molecular geometry. We have linear geometry from an AB2. We have trigonal planar geometry from an AB3. AB3 and AB4 geometry gives us a tetrahedral shape, and AB5 gives us a trigonal bipyramidal shape, while an AB6 gives us an octahedral. The final molecular geometry will be influenced by whether or not the electron pair regions are filled with atoms or whether they are filled with a combination of atoms and electrons. A trigonal planar geometry will have either a trigonal planar molecular geometry or a bent geometry. A tetrahedral arrangement of electron pairs can give a tetrahedral molecular geometry, which means it has all bonded pairs around the central atom, or with the substitution of a single electron pair, it becomes trigonal pyramidal. If that tetrahedral geometry is further substituted with another lone pair for two lone pairs and two atoms, it becomes a bent geometry. A distorted tetrahedron geometry results when there's an AB4E arrangement of electron pairs, in which four bonded groups are present and one lone pair is there. If we further substitute that distorted tetrahedron with one more lone pair, giving us an AB3E2 arrangement of electron pairs, we get a T-shaped, although its electron pair arrangement is still trigonal bipyramidal. Its molecular geometry is T-shaped. That T-shape becomes linear when we move to an AB2E3 geometry. In the octahedral arrangement of electron pairs, an AB6 becomes a square pyramidal by substitution of one electron pair for 5 atoms and one lone pair. If 2 electron pairs are substituted, it is energetically more favorable to have those completely opposite, resulting in a square planar geometry, with the 2 electron pairs completely opposite and the 4 bonded groups being located 90 degrees apart. So, there you have it, Chapter 8, Lecture 1, Advanced Theories of Covalent Bonding, Lecture 1 of Chapter 8.